Hi everybody, I am Alessio Perinelli from the University of Trento, and today I would like to discuss about a work that was carried out by myself, Veronica Mazza, Michele Castelluzzo, and Leonardo Ricci concerning a crucial issue in the investigation of complex systems, namely the estimation of connectivity between nodes in a complex system, in a network, by relying on scalar time series measured, one scalar time series is measured for each node. Now, some examples of this issue are, for example, the human brain, in which you can measure activity corresponding to different areas or nodes by relying on electroencephalography or magnetoencephalography. And another example is climate or the atmosphere system, if you want, in which you measure temperature, pressure, or wind speed. Now, in all those cases, what we need to do is to find an algorithm, a machine, to infer links out of the measured scalar time series. And this is the topic of the present work. Now, we propose a method which we call the CTO method, and I will explain why in a second. And the method relies on cross-correlation between the scalar time series, which, however, we assess on running windows of different width. So given a window, we compute the cross-correlation coefficient between the two scalar time series, and this we can do it for different width of the window, of the running window. The result is that we have a cross-correlation coefficient that is both a function of time along the time series and is also a function of the window width that we use to compute cross-correlation. So the resulting object that we have is a so-called cross-correlation diagram, in which we have two axes, the time axis and the window width axis. Now, this is why a cross-correlation is why the method is called CTO, because CTO stands for cross-correlation timescale of observability. Now we have seen why cross-correlation, but we still need to understand why we call it timescale of observability. First, we need to assign a significance to the cross-correlation that we observe, because cross-correlation by itself is merely a number between plus minus 1. So to do this significance estimation, we go beyond a very simple Gaussian null hypothesis, because we want to take into account also the possibility that the underlying signals are autocorrelated, and they can also have distribution of amplitude that is definitely different from a Gaussian one. So instead, we use a surrogate-based significance estimation. The surrogate algorithm that we consider is IAFT, that stands for Iterative Amplitude Adjusted Fourier Transform. And the goal of the algorithm is to preserve the amplitude distribution of the two of the time series, and to approximately preserve also the autocorrelation. So by relying on the surrogate-based significance estimation, a cross-correlation diagram is transformed into a diagram of p-values, which are probabilities and therefore have a clearer interpretation. Now, this is still a diagram, so a two-dimensional object. Now we want to go to a one-dimensional object. And this object is what we call an efficiency function. Now the efficiency function is defined as the number of windows given a certain width that exhibit a significance cross-correlation, which means the p-value is below some significance threshold, say 5%, and divided by the number of the total number of available windows. As a consequence, this efficiency function is bounded between 0 and 1, which is the reason why we call it efficiency. Now, different diagrams, as you can see in this slide, different diagrams produce different efficiency functions. Some of them are just quite flat just above 0 because there is basically no cross correlation for any window width. Other ones are, for other diagrams, the efficiency rises above and can get up to 1. Now, what we do then is to consider a threshold, an efficiency threshold, which we set, for example, to 50%, and we consider the window width, capital W, at which the efficiency crosses this threshold. Now, it can be that the efficiency never crosses that threshold, and in that case, capital W is not available. Now, this capital W is what we call the time scale of observability, which is the missing part of the name of the CTO method that I mentioned before. So at this point, given a pair of nodes, and so a pair of time series, we have a time scale of observability, W, which is a number measured in seconds, for example, which is a measure of time. And okay, so this approach was, for example, used by our group to assess cross correlation in brain networks by relying on magnetoencephalography recordings. And this is the first article in which the method was proposed and applied to this kind of recordings. But a key question at this point is, okay, how reliable is the CTO method? Now, since the more two time series are correlated, the smaller we expect to be the time scale of observability of this correlation, we can say that W to the -1 provides an estimate of connectivity strength. So the larger W to the -1, the more connected two nodes are. Therefore, a possible test bench that we can use as a comparison for to test our CTO method is mutual information, which shares some similarities with our method. For example, they are both symmetric for exchange of the two time series and non-parametric thanks to the surrogate-based significance estimation that I mentioned before. Now, we can then just compute on some test time series we carry out the analysis with the CTO method, we get our W to the -1, and then we also estimate mutual information by relying, for example, in this work, on the K nearest neighbor estimator. Okay, so what happens is that we carried out this investigation, and which is discussed in the work that you see here, which was accepted for publication in Chaos. And what we found, for example, here you see the picture for a case study with magnetoencephalography recordings again, and you see that the joint distribution of W to the -1 and mutual information shows definitely that there is a dependence between the two, or at least a relationship between the two quantities. And if you compute the average, you see that the curve is almost linear in a log-log scale. And therefore, a power law links our W to the -1 to mutual information. And indeed, this power law is well explained by a simple model of delta-like shared events superimposed to a Gaussian noise. Just a couple of other examples. Here you see the data for EEG recordings. So again, human brain in electrophysiological recordings of human brain, and also for a completely different system, which is the atmosphere. Here you see the results for wind speed recordings. Now, the different curves that you see in these graphs correspond to different efficiency threshold. I have no time to go into details of that, but also this shift between these curves is also explained by the model of delta-like shared events. Now, finally, I just leave you with some references, and of course, you feel free to contact us. Here you see our email addresses and our website. So thank you very much for your attention.